Okay, in this lecture I'm going to introduce the conversion constructor, which is a constructor that will convert a single argument of a different type into the constructor's class type. You can see a conversion constructor prototype. The formal parameter is a reference to class B constant, whereas the constructor's class type is class A. Okay, so the goal of that constructor is to convert the argument, which will be of type class B, into the type of class A. I'm using the vector structs again for this example. You have a vector 3D struct, alright, we have the default constructor, and for the vector 3D I also have this constructor right here that takes in 3 arguments. We have 3 members here, float x, y, and z. And then we also have a vector 2D struct. This has x and y for its members. This again is 2D, so for that we don't care about depth. So in other words, we don't care about the z-axis and that z value. Okay, we only care about x and y. And let's say for memory utilization reasons, we want to convert between 3D and 2D vectors. Okay, we have the default constructor and then we have a conversion constructor as well. So the argument that this will accept is a vector 3D. And I just call that vec3p for vector 3 parameter. Alright, and that's how we're going to convert from vector 3D to vector 2D. We completely ignore the z element. And in main, just as a quick example, I have a vector 3D called vec3. I pass in these 3 arguments to construct the object, and then I have a vector 2D object, vec2, and I pass in vec3. Okay, so this is going to initialize a vec2 to vec3. Okay, and because of that we have to do a conversion. Then I simply do cout vec2.y to print out the y component. You can print out x2 if you want. And that prints out 5. If I comment out this conversion constructor, then we'll get an error. No instance of constructor vector2d matches the argument list. Argument types are vector3. If you try and build and run, you'll get an error. No user-defined conversion operator available that can perform this conversion. Alright. And so that is why we need this conversion constructor. The next section is going to deal with implicit conversion and the explicit keyword. And when I refer to implicit conversion, I'm referring to automatic conversion basically by the compiler, whereas explicit conversion means that the programmer explicitly specifies what the conversion should be, typically by using casting, as I talked about in previous lectures and in previous lessons. Sometimes you don't want implicit conversion, in other words, you want to avoid that implicit conversion and only allow explicit conversion. And that is where the explicit keyword comes in handy. It specifies that the constructor cannot be used for implicit conversions. Now this affects copy initialization and forces explicit construction or initialization, and it's best to show you what I mean by this in Visual Studio just in case you are struggling to recall what I mean by copy initialization. And this is the prototype for the constructor. You use the explicit keyword followed by the class name and then the formal parameters. I have a different example for you here. We are simply using the vector2d struct and I have these 2 constructors. I'm writing each one of those on a single line just because we have nothing really in the body since we are using the initialization list, and so that I can get more stuff on the screen. As soon as I add something in the body, then of course I'll go and I'll put the initialization list on the next line and I'll break open the body again. Alright, so this is the default constructor. It is a vector2d, so we have x and y. And then I also have a second constructor here. And in this example, it has a single formal parameter, a float, so it takes in 1 float, okay, inf for input float, and it's going to initialize x and y to that single float. We are familiar with this sort of thing. I construct vec, which is a vector2d, and I pass in the single argument, and that's going to initialize the x and y components to 5 now. Prints out 5 and 5 for x and y respectively. We can also do this sort of initialization, so I do vec right here, I construct vec, and then I initialize that to vec here. That works as we expect. But another thing you can do is, you can actually also initialize vec like this. You can construct vec right here, and you initialize it to this. Alright, I'll print this out to make sure that we can see this conversion constructor is gonna get invoked. Conversion constructor invoked, and then 5 and 5. I'll continue here and I'll overload the addition operator as a global function. It returns a vector 2D. We have operator, the addition symbol. I don't have an overloaded constructor here that accepts both x and y components, so I'll do a temp, and then I'll do the addition of the x components and the y components for the left and right hand operands. Alright, I'll assign those to temp, and then I'll simply return temp again. I'll do something simple like this. I'll add the literal float right here, 3, to vector, and then I'll assign that back to vector again. That will call the conversion constructor twice. Once right here, where it constructs this object, and then once right here as well. Remember, this float here is just a literal. It is just a temporary, it's not a vector 2D. The operator that we overloaded right here detects in 2 arguments, and both of those has to be vectors. So it's going to use the conversion constructor to convert the float 3 into a vector. Another thing I'd like to notice, if this was a member function, this operator right here, I'll actually just copy that, comment that out. Okay, and we can do something like this now. So I have the operator overloaded, and if I go down here, you will see we get an error. No operator, the addition operator symbol matches these operands. Operand types are float plus vector 2D. Okay, this will not compile. But this line here will compile. And why is that? That is because these binary operators, when overloaded as member functions, expect the left-hand operand to be of the same type as the class, so in this case vector 2D, right, the same type as the calling object. And I just wanted to mention that. And that is why I overloaded it as a global function, so that it can take in both the left-hand operand and the right-hand operand independently, and I can swap these things around if I want. So just another bonus example for you on overloading operators as global functions. And one of the reasons, or one of the situations where you would overload operators globally instead of overloading them as member functions. Okay, let's say we want to prevent this, because I can actually use maybe an integer here as well. I'll scroll up. I'll specify this conversion constructor as an explicit constructor. And now back in main, all of a sudden you'll see a bunch of red squigglies. Constructor for struct vector 2D is declared explicit. Previously this 5 was converted to a vector 2D, and then right here in the second statement, the same thing goes for that left-hand operand, this 3 float. Previously that was converted to a vector 2D also, which is necessary for this overloaded operator. Now those conversions previously were implicit. Okay, so the compiler basically converted those automatically for us behind the scenes. But now, since this constructor right here is specified as explicit, we now have to make more explicit constructions. What you can do is, this right here is an explicit conversion, and it will explicitly go and create temporary vector 2D objects. Build and run, and that should work fine, as you can see. But for this first statement here, that is unnecessary. What you can do instead is that right there. Okay, so this type of conversion is a bit more subtle than what we did previously from the vector 3D to the vector 2D, because we are not converting from one user-defined type to another user-defined type. We are simply converting or constructing a new object by using the fundamental types. Something that is less common but that I thought might be interesting to you is conversion operators or functions. The syntax for this is a bit weird. You'll notice that we have operator and then type, followed by a semicolon, and then the body. What's going to happen is you are going to convert an object to the specified type, such as an integer or a float, for example. And this is often used implicitly, but it can be specified to be explicit as well. As we can see from the example, this has no return type and it takes no arguments. Right, we only have operator and int, followed by parentheses. It takes no arguments. So in other words, it has no formal parameters. That type, so in this case integer, is going to match whatever it is that this returns. The syntax for this is a bit weird, is a bit more abstract than what we are used to. So we'll start with this concise example. We have the entity class again. In the public section, I have a constructor, and it's such a simple constructor. I write it on one line just to keep the example concise, right? Next, we have the conversion operator or the conversion function. Notice again, this does not have a return type like previous operators will have, such as the addition operator, for example, and so on. And here, instead of having a symbol such as the addition or multiplication symbols and so on, we have the type that we want to convert to. So in this case, when we use this, we want to convert entity to an integer. And this is const because it's not going to modify the state of the calling object. And this is going to return member. And that is basically how we can convert an object or an instance of type entity to an integer, is by returning the member. Okay, let's look at where this is handy. I construct entity 1. I pass in 55 as an argument for the constructor. So that is going to initialize member to 55. Note that no stream insertion operator is defined for the entity class, but of course there is one for the fundamental types, such as integers and so on. So when we do a statement like this console output entity 1 member. So the member of entity 1 is entity 1. So this is an object, and again we do not have a stream insertion operator overloaded for this object, but there is a stream insertion operator defined for integers, right? So what's going to happen, the compiler is going to use conversion here. This conversion is implied currently. So we want to convert entity 1 to what? To an integer. So it's going to do that conversion to an integer. It's going to fetch that value 55, and then it's going to do the insertion operation. Member is 55. As I mentioned, you can also specify this to be explicit. And now you'll get an error here, so what you have to do is, you have to do explicit conversion, or in other words casting. Remember that previously we did implicit conversion. And how do we do that? If you think for a second, it's going to be the same, the same thing that we've done in previous videos. To convert the current type or the object to entity 1. What is the type for entity 1? Well, that is a type of entity, and we want to convert that type to an integer. So do int between parentheses, and that will do that conversion, and it's going to use this right here. If we build around that, you can see that works fine. And if I comment that out, this conversion no longer works. No suitable conversion function or conversion operator from entity to int exists. So now you know how to do that, how to define a conversion operator. One final example. I'll go and uncomment that. Okay, now you can do interesting things like this. You can have an integer x, for example, and we can assign entity 1 to that now. Okay, so this conversion, and then I can simply print it out again. What you can do is, as I mentioned, if you want the ability to use this implicitly, then you can do that. Remove that explicit specifier, and now we can use that implicitly, and it prints out 55 just as we would expect. Okay, you're gonna decide on that by a case-by-case basis whether or not you want that to be specified as explicit. As another example, I'll use the vector 3D and the vector 2D again. We've seen the definitions in a previous subsection. For the vector 3D, I have these constructors and the x, y, and z members. Then for vector 2D, I modified the constructor. It has a default argument, and it will initialize both components x and y to whatever argument we pass in, or to the default argument. Then I have the conversion constructor, and then I also have a conversion operator or function. For the conversion operator, it's going to convert a type of vector 2D to a vector 3D. And how do we do that? In the body, I'm going to print this out, conversion function invoked, and then I'm going to return this right here, a vector 3D. For vector 3D, remember we have this constructor that takes in 3 arguments. So I construct a vector 3D right here. I pass in x and y and 0. X and y will come from the object that we are converting, which will be a vector 2D. If we take a closer look at the conversion constructor and the conversion operator, in the conversion constructor, we are converting a vector 3D, which this conversion constructor takes in as an argument. We are converting that vector 3D to a vector 2D. Whereas with the conversion operator, we are converting from a vector 2D to a vector 3D. Right, so we are doing the opposite. And that is important because if we want to have a conversion constructor, let's say going in both directions, so we want a conversion constructor for vector 3D instead of having a conversion operator here in vector 2D. Let's say we want something similar, so conversion constructor from vector 2D to vector 3D right here in vector 3D. We could run into issues. We could do a forward declaration, for example, and then do the conversion constructor definition. Because remember that is now going to take in a vector 2D then, but vector 2D is defined down here, not up here somewhere. So you can do a forward declaration for vector 2D, but within the definition you're going to use the member. So you're going to do vector 2p, for example, .x and so on. And because of that, you'll get errors. Okay, so as I mentioned previously, it's fine if you declare a variable or something like that, but once you start to use the members, you'll get errors unless you have the entire thing defined before you use it. Let's say if you cut and paste vector 2D before vector 3D, then you'll have a problem with this one right here again. So you'll have a problem with the conversion constructor from vector 3D to vector 2D. And so because of that, it's easier to have the conversion operator. By using a conversion constructor and a conversion operator, you can now convert from a vector 3D to a vector 2D, and you can also convert from a vector 2D to a vector 3D. Now, I'm actually not going to use the conversion constructor for this demonstration, so I'll just comment that out. So we are using the conversion operator. In main, I construct vec3, which is of type vector 3D, and vec2, which is of type vector 2D. For vec3, I pass in these arguments for the constructor, and for vec2, I pass in this argument right here. For vec2 here, the x and y components are both going to be 5.5. Then I do this assignment, I assign vec2 to vec3. Since these are not of the same type, there's going to be an implicit conversion. Vec2 is going to get converted to a vec3. Okay, so it's going to use this conversion operator, and it's going to construct vec3d here, passing in the x and y components of vec2, and then it's going to return that. So this right here is basically going to get replaced by a temporary vector 3d, which is then going to get assigned to vector 3. Now we actually do not have an overloaded assignment operator, so of course the compiler is just going to generate a default one, and it's going to do member-wise assignment. So it's simply going to copy the members over from the temporary vector 3d to the vector 3 here. And then we simply do console output vec3.y. And the same for vec3.x. That gives us 5.5. And if we do vec3.z, we should get 0. And that prints out 0 as we expect, because of this construction. So again, we do x and y, and then for z, since a vector 2D does not have a z component, we simply pass in 0. Alright, I hope you found this section interesting. You can also define a conversion assignment operator, which as you can see will take in class B as an argument and then return a reference to a class A. Just a quick example for you. I have the vector 3D again. I have these two constructors. Then I have vector 2D. For this example, I removed the conversion operator and the conversion constructor. Then main, I do these constructions again. And now I'm trying to assign vector 3 to vector 2. But I'm getting an error here. No operator matches these operands. And following that, I'm trying to print out, so I'm doing console output vector2.x. So let's go and overload that assignment operator in the vector 2D definition. As with the previous examples and the previous assignment operators that we overloaded, this is going to return a reference to the calling object by dereferencing this and returning a reference right here. And we simply do these assignments, the right-hand operand .x, which is going to be the vector 3D, so we get the x from that and assign that to x, and the same with y. Now if you are trying to do this with classes, then you might have to go and define getters, because we don't overload the assignment operator as a friend, it is overloaded as a member function. Back in main, now this statement here will work. Build and run, and that prints out 3. Where we construct vector 3, we pass in 3 for the argument for the x component, and so when we do this assignment, of course vec2.x should also give us 3. Okay, that is going to wrap up this lecture.